Okay, big three kinematic equations. So let's refresh what those are. The first one, x final equals x original plus v original t plus 1/2 acceleration times time squared. V final equals v original plus at, and v final squared equals v original squared plus 2a delta x. So x's or y's represent position. So this is a review from things we did earlier in the year. V's are velocities. A is acceleration. And t is time. So I'll give you a minute to consider that and get those notes rewritten because we've done this once already this year. So we're going to do it again. We shall do this again. This time, hopefully, it'll be easier the second time through. That's the goal. Actually, let's leave that up. I'm probably going to need that today. So these same big, scary looking equations that we've had in the past. But now they're going to be less scary because we've gotten better at using formulas a little bit. And we've gotten used to these symbols. We've seen them a lot. So hopefully these will be a lot easier this time through. So what is it that we're going to do? We're going to do projectile motion. And the thing about projectile motion is really it's just two-dimensional motion. So a projectile is an object launched at some angle with the ground. So projectiles, any object that is launched at some angle to the ground. So a football being kicked off in a football game, or a football being kicked up for a field goal or an extra point. Poor Eagles kicker that can't make the extra point. You never see that happen in the pros. So like last night I was grading, they're like, he missed it. And I'm like, what he missed is an extra point. And I'm like, the Eagles are having a year. I'm not an Eagles fan. I'm a Steelers fan, so I'm super, super happy. It's been a long time since we've been good. Really, really good, that is. So kind of fun. All right, so any object launched at some angle with the ground. So if Autumn was to throw a softball to Lauren, they were playing catch this afternoon. She throws a softball to Lauren. Is that a projectile? Yep. Is a cannonball being shot out of a cannon a projectile? Yep. What about dropping a wrench off the rooftop of the school building? Does that one count? It's going to go straight down, yeah. Okay, so you don't like that one, but if we kicked it off the top of the building. Okay. All right, so actually both of those are going to be considered projectiles because here's what the catch is going to be. Projectile motion. Oh, hey, spell that word. We can do it. We can spell today. No, we can't. We can spell, but we can't write. Okay. School is hard. Okay, projectile motion. Hey, let's put an L in that word too. That'll be good. Any object whose only acting force is gravity. In other words, any object, the free body diagram will always look like this. Something with gravity down. That's it. That's a projectile. And I know some of you are thinking right now, but Miss Wilson, isn't it also a projectile if there's air resistance? And the answer there is not in this class. Not in this class. Okay, so yes, that's a good question. What Juliet just asked for those of you at home is, but if I kick something off a building, like if I kick the football or I throw the wrench, isn't there a force acting? Projectile motion, the assumption we're making is that has already occurred. The problem starts when you do whatever it is you do. Right after that starts from the rest of the problem. So for kicking a football, if Dylan was to run up and kick the football, after he has kicked it, it is now moving up and out at some angle. It would, that original force that started the motion is not considered part of our problem. Okay, so we're looking at it after it's already moving and in the air. And then the rest of the time, the only force acting on it would be gravity. So what is going to be the shape of the path? What kind of paths will we see? What does the position time graph look like? Yep. So we can see one of these. Actually, let's not make that specific. Let's just make this position time. So for the typical one, it would be goes up and comes back down. Parabola. I think I can probably do a little better than that. But so it will be your normal. There we go. That's a better parabola. Goes up, comes down. What else could we have? We could have just one arm of the parabola. Or we could do sort of an in-betweener. Something like that. So in essence, what do you always get? Part or whole parabola. So your position time graph is going to look like a parabola. Unless, I know some of you are just like, no catches today, Miss Wilson. I'm not back from Turkey. Not mentally competent enough to handle non-Turkey thinking. So here's where this gets tricky. Is this a vertical motion or is this a horizontal motion? That graph that we just made, is that vertical position or horizontal position? Could it be both? Could it be neither? Okay, so if we look at it, if we look at the motion, Let's just say a football kickoff. How does the football move? Up and out. So this would be the actual physical path that it takes. This is the physical path. What happens with the vertical part only? So if we were to, when we're looking at this, and I look at a football being kicked or a football in the air, it's going to go up and come back down while it travels horizontally across. But what if I only look at the vertical motion? What does it do? Come down here and scroll down. Come on, there we go. So if we do the Y motion, what does it do? It goes up and it comes back down, right? Because this axis is time. So as time passes, the Y value gets bigger and then the Y value gets smaller. Everybody okay with that? What's happening horizontally? We're moving forward. Do we move forward the whole time? Have you ever seen somebody kick a football and it goes over there and then it comes back here? Not if you let it bounce. No letting it bounce, that's an extra force. So this would be like that. It is constantly moving forward. So this part up here is overall motion. This is vertical motion. And this is horizontal motion. Okay. So let's go over here. And check out the news. No, let's not check out the news. The election is over, right? Do I have to listen to election news every day for the rest of my life? Regardless of which side you're on, I'm done. Just we're good. Let's go. Okay, so come on, sweetheart, you can do it. We're gonna think and talk for a few minutes, not so much draw. Maybe we'll see what my computer's gonna do. See how this plays out. I do not have infinite patience today, Fit. You're making me unhappy. Yeah. No. Okay. You know what? I can draw myself. Okay, so let's just start with this. We have a cannon on wheels. Yes. Do you know what the cannon holder is called? Come on, military folks, you can do it. It's called a caisson. Caisson. So it holds the cannon so that when you shoot the cannon, what does the cannon do? It rolls back a little bit. Also, they put wheels on the bottom so that they could turn it backwards and haul it somewhere, because freaking heavy to carry a cannon to some location. Anyway, so I got a cannon, and I'm going to launch this at various angles. So if we trace this back, some angle down here, it can be changed. So you guys probably already know the answer to this question, but my first question is, if I want it to go the farthest horizontally, from here to here is called the range. How far it travels from where you shoot it to where it lands is called the range. So what angle would I need for the furthest or biggest range? What do we think? Where did my chat box go? People out there or people in here, feel free to jump in. What is the best angle for the most range? Okay, I'm hearing 45 degrees. Anybody have an idea why 45 degrees? Well, what would be the worst angle to shoot at? 90 degrees would be the worst. 90 degrees, or there's another one. Oh, 90 degrees or 0 degrees. Why would those be bad? So if you shoot at 90 degrees, you shoot the cannon straight up in the air and the cannonball comes back on you. That's a bad plan. I don't like that plan. So it doesn't move forward at all. And if I shoot it directly across, it only has to fall like this far. So yeah, it hits the ground like barely in front of the cannon, which unless you're trying to kill your teammates, that's a bad plan. But friendly fire is a real thing. Those of you that know anything about military know that friendly fire is a real problem sometimes. Friendly fire is where you shoot at the enemy, but you kill your own people. That would be considered a boo-boo. Depending on which end of the shooting you're on, it's either a little boo-boo or a really big boo-boo. Okay? So what about, so the longest range is going to be 45. And here's how you have to think about this. When I launch this cannon at this cannonball at some speed, let's say that we launch it at 30 meters per second. It's a little less than 100 miles an hour. Okay? That's a little low for an artillery shell, just so you know. Bullets go about 750 miles an hour. Some of them. Artillery shells go several hundred miles an hour. So this would be like a low fat cannonball. But if I shoot at 30 meters per second, it's going up and to the right, which means not all of the speed goes into moving forward and not all of the speed goes into moving upward. So the game you play with projectile motion is this. If I want it to go way down there, where do I want most of my speed to be located? If I want a big range, I want most of the speed to be a forward speed. But I also need it to stay in the air, right? I don't want it hitting the ground really quickly. So I don't put all my speed this way, because if I put all my speed straight forward, it just goes plunk on the ground. I need some of the speed to go up so that it goes up and down, which gives me more time in the air. Does that make sense? So I'm in this, I want it to go far that way, but I also need it to stay in the air. And so the 45-degree angle sort of splits that evenly. Now, it does not give half of the speed up and half of the speed across, because some of you may recall that if we take this, let's think of this, if you think of this as a triangle, (30 meters per second), and this angle is 45, you guys might know that this is not 15 and 15. It's not 15 and 15, because what would that do? What would that make this side? Remember the cute little Pythagorean theorem? So if this was 15 squared plus 15 squared, this does not equal 30 squared. This is 225 plus 225 does not equal 900. Okay? So you don't get half the speed. But you do get that these two speeds would be the same. X and Y would be equal, but they're not half. They're equal to each other, but they're not half. Okay? So 45 degrees without air resistance is the best angle. What if we had air resistance? Do you have an idea what you think might happen if we have air resistance? You think it's going to be bigger or smaller than 45? I'm hearing smaller. Okay, so what was the reason? Okay, since you have drag or air resistance, you're losing energy to friction. So somehow you need it to go further, so you should probably make the horizontal piece get bigger. If I make a horizontal piece get bigger than the vertical piece, what does that do to my angle? Like the horizontal get bigger than the vertical, then the angle goes down. In fact, as a person who used to be a shot putter in high school, made state in that, made state in discus, the best angle is about 42.5 degrees. Now, do you think that was useful to me as a shot putter? In my head, doing that calculation seemed like a really smart thing to do, because then I'd be, figuring out how to do this better than the other people. Yeah. It's really hard to do something like that at that exact same angle over and over again. But for my benefit, at least it knew me where to sort of start reaching for. So here's another thing about projectile motion. We have this idea of max height. Let's take that out and over. Let me do another picture. Oh, let's talk about this max height. At what time does max height occur? If object is launched from the ground. So if this whole time, let's say from here to here, it takes you time equals t seconds, what would the maximum height occur at? Half t? 3/4 t? Half t? What shape did we say this was? Parabola. What's something parabolas have? Well, one of the things they have is a vertex. The vertex here would be called the maximum height. And what's true about the left arm and the right arm? They're symmetrical. So they are symmetric. So the time to max height would be 1/2 of the total t. Is that still true if I throw something off a cliff? If I throw something off a cliff, now is that still true? No, because you've already got some height. So it only has to go a little bit more to get to the top, and it spends a lot more time going down than it did going up. Okay with that? But what controls the time in the air? The vertical speed and gravity control time in the air. Okay. What else is true at the maximum height? There's one other key feature. There's one more piece of physics that we can use there. When we get to this maximum height, how fast are we going? Like if I launch it at some speed, what happens as I go up and come back down? Well, let's simplify that a little bit. What happens to the vertical part of the speed when I'm going up and coming back down? Let's say the vertical part of the speed is 40 meters per second. What happens? I start at 40 meters per second up, then I'm at, after 1 second, what's gravity? What's gravity's acceleration? Down 10. So I go 40 meters per second, then 30 meters per second, then 20 meters per second, then 0 meters per second. Vertically. Max height has vertical speed equals 0. What about horizontal speed? Does Jacob take a baseball and he winds up and throws it, and it gets to the max height and it falls straight down? Is your horizontal speed 0? Because it keeps going forward, right? In fact, the other part about projectile motion, so that's one of our key features, and the other one is this, and I'm out of space, so let me give myself another page. Come on. No, really, I asked, well, let's just stick it here. Horizontal speed never changes. After launch. And why is that true? You have no air resistance. Okay. It's a lot of notes for one day. We're going to work on this for a few days, not just one day. But preview of things to come. Preview of things to come. Tomorrow's a work day, right? Tomorrow's Wednesday. Yeah, tomorrow's Wednesday. On Thursday, we're going to pick back up with this, and we're going to start working some practice problems, because the best way to work these out is to work these out. But what you're going to have to remember is these 3 kinematic equations that we started with, you're going to use all those again. But guess what you get to do? For every problem, you get to do them twice. Why do you get to do them twice? Because there's horizontal and vertical stuff going on simultaneously. So you'll do stuff with vertical, you'll do stuff with horizontal. Guess what happens when you get done with doing this twice every time? You get really good at it. Those equations that were scary and hard and didn't, you remember those? The struggle that we spent on that? Some of you don't. When we start working them, you will. But it's a review. It's something we've already done. So this is the second time through. So hopefully it'll be a little better this time through. Okay. So now I'm going to let you guys go if you would like to go, or stay if you would like to stay. I'm going to go help Nathan for just a few minutes, and then I'll be back up here. And I'll give you, yeah, what you need. This way? Is that good? Okay. If anybody else needs to move it up or down, the mouse is up here. Feel free to do that. Okay. Okay, Nathan, let's talk. Okay, so what is this? You return a laptop to me with this charger and this power cable?
That's awesome.
You are not fooling me, little kiddo. Okay. So this one is it has the same formula basically as this one. But now you have a different constant. So it's not called a spring constant. It's a torsional constant. Okay. But it is just a number, and let's see what it is. I didn't know. Oh, that's what phosphorus and indices are. It's just the rotate, you have to have a different constant because of rotating mass. You don't have it in there. Okay. And just leave it there. I really think something like, this is K, the English word K. But I want to say this is K. Okay. I feel so bad that you guys spent 2 hours working on that graph.
We did, and we didn't even notice until we gotten done with it, and then we looked at the clock and it was like 5.
Yeah. Well, I felt bad because I was like, where did they go? And then I thought it was me. And by the time I got logged back in, I still couldn't get you guys. So I figured it must have been some sort of technical issue. Okay.
Wasn't a big.
I do appreciate that. The last chapter was physics 3 mechanics. Okay.
Do other physics classes just do mechanics like all year and they take one mechanics stuff?
Yep. And you know what? My kids always scored all that. So you're doing as well doing it this way is the kids are taking the whole year to do it. I don't understand that. But I think most schools do that. This is one of y'all's tests for sure. Yeah, if you need to leave for impact time, feel free. Yes, yes. Yes, and then Jan for you.
Yeah, exactly.
Okay, so this is. On Earth, we need to tell you 1.8 or 1 on average. But, even for human gravitation, is that gravitational constant, I'm gonna have to go to 1, I'm gonna have to go to 2, I'm gonna go to separation between. So. Yep.
Okay,
Well, we got it because we
Oh, we were supposed to bring a picture of ourselves to the wellness class, and I didn't bring one, so I just like.
Okay, this is a really good job here. It's giving me very much, quadratic. I understand.
people knew that, like, they tested his math.
It's my favorite kind of art.
Yeah, it's very.
But what they couldn't figure out is how to, like, do some of the experiments to show that. So the experiments that was done, was by Kennedy.
Well, actually, not right now.
Did you see what you got on the chemistry?
Basically what he did
I got a 63.
was he took,
Yeah. In the last part, I said, I'm not supposed to play question. I'm not letting I said, hey, sis, they don't have them down. Yeah, I saw that I got it done, but I understand how to get it. Yeah. I don't know. I think the last one said was not there.
So like,
he took
there's gonna
another
be a
bar,
curve. There's gonna be a curve.
Okay.
I mean, at least I think.
and then one more started.
You know, actually, did she curve the body quiz for you?
She never put it in.
Yeah.
She put it in for me.
The mommy said the mommy said.
The one that everybody failed, and everybody was mad at me for, like, not.
Oh, yeah. I don't know. Well, I've only looked at like, I feel like before the circle, 28 out of 54.
You actually did better than I did.
What is 28 out of 54?
Oh, you actually did. Wait,
I got 51.
This one,
I don't mind. I got a 34.
and he released it from there.
Yeah, you got it.
He returned, which was completely.
Yeah, you got 51. Well done, yeah. Especially for the world.
I have 6 hours.
If you look down at the top,
When did you get this? When did you get
what
this?
you see, it started like this.
Like,
You can hear how.
Then you would run this way.
I am. I don't like that. I'm not even like really.
Oh, you're recording? Oh, okay.
I'm taking art.
Very much hip to be different size.
And then I'm asking, and then my friend asked me to, he's an interesting guy.
So.
I mean, a lot of good colleges, like all three of the colleges.
I read it. I don't push it on it.
The more.
Feel like we're down here. Huh?
Yeah, what I probably never learned.
John Porter.
But it's something like.
I don't drive.
You can do anything to touch your
Well,
mind.
because it's something that you can electrostatic force,
Oh my God, this is giving me very much,
pushes back out the other.
who put devil horns on the very cone?
Oh,
It was very,
Cars.
Hard. Very much three-dimensional. Shadow,
and
shading.
this, we would kind of run that to run the
I usually,
especially when it hit. Make it important.
no.
really low mass, very lightweight mass, dry.
Never been
It's
sure.
very small mass.
Because I was literally just.
Plant these.
Oh, just now. Okay, I could do
You can measure that kind of rotation, you know, the mass that you can figure out how much gravitation is.
It's great.
It's really nice.
Oh my gosh, I didn't.
But one of the things we did after that was people wanted to know two things that we wanted to know. What is mass here? And then the second question is, what is the radius here?
Maybe it's been my.
Oh, yeah, I never did.
I think I showed you guys the Apple video with Carl saying it was doing how we do the original measurement of your radius. Yeah, no, okay. So. You could, in 2000 BC, 2000 to 1000 BC, a guy named, what is his name? I have his name. But, anyway, he lived in Egypt. And so what he did was, and here was another city, like, but in another city, Alexandria. Because Alexandria, huge center of learning at the time. So what they did was they formed two states in the ground. One at Cairo, one at Alexandria. Curve is curved, I knew they would come this far back. The sun, being here, makes the shadow on this one. Here. And makes the shadow on that one. There. So you could figure out what the angle was doing. Okay? That angle would have to match the curvature of the earth. Because instead of having two posts sitting like this, you have two posts sitting like this, but on the curved surface. The difference in the length of shadows would therefore give you how much curvature you have.
Okay. I see where you're going with that. I don't see the exact calculation, but I see how
Yeah.
they would.
And so then they use the idea that the circumference of the circle is 2 times 5 times radius, and we've had that forever. They didn't know what pi was, they estimated at various values, but, so they're about 15% off in their calculation, but ridiculously good. So they used this idea, and that gave them radius. Once they did the radius, with the spring, you can measure the weight of the ion the spring scale. So then they do this, and then this, is the object you're working with, and so if you measure, they can find that this new research predicting it, and then we revised, he got changed a lot. He was updated and improved, and updated and improved, until we're at the point where it's done. Okay?
What was the last one that was updated?
I don't know, not, I mean, they do it every so often when they get a better tool to measure, but really, I don't think it's changed by something in the billionth place. So, yeah, obviously, beginning wise, it would be like 7 or 8, and then 7, well, 6.9 is fine, but, well, 6 is too low. So interesting things, a lot of it. One of the interesting, another thing. One of the things I'm looking for is that, well, he,
You'll pay one for
that's
the
what
call?
you do on research.
Yeah, that's the one.
to do?
And you just like something that.
Okay. Okay. Yeah, excellent.
Okay, hey guys, one of my friends is having a capstone presentation right now, it's about, aviation. And he needs more people, so if you guys aren't doing anything, it's,
Can you go and help watch?
yeah, it's in Miss Fallon's room. So, yeah.
Anyway.
I mean, I got to think it's like, you guys can probably do that.
That this would be true for these plants. Well, clearly we haven't gone to. But we can calculate it based on how the other objects in the solar system measure and rotate and all those things, we can figure out which one is experimental. When that's dangerous. We can get the radius keeper, if we can do a telescope and engineer that pretty close now. And so that would be the gravity keeper. So this is true for any planet. It would just be gravitational constant universe, mass of whatever the flighty is that you're orbiting. Like we're all orbiting the Earth more closely than we are the Sun. And then the radius of the Earth would be from the center of the Earth to the location of the planet. Okay? The other thing that that helps with is what's going to change for us, because this is all we did all this in 2
I remember doing that.
Yeah, the part that changes is this, because this G is not constant because it depends on that radius. The value of D at any moment in time is from center of the Earth to the center of the Earth, or whatever planet you're working with, to the radius of your satellite or your object or your massive rock or whatever you're looking at. And you will do that as V, mass of the planet, over R squared.
Okay.
So these two get pulled out. Right? And you get one of R squared. Which is easy to do, because that's R to the negative 2, so that would be R to the negative 1 over negative 1. That was part of it, yeah. Which then means that if you want to do gravitational potential energy, so now we're in a situation where we're gonna have to get all of this in terms of R. So the cool part is, if we do that, we could be, this mass is what mass is, the object or the Earth? It's the object. That's not gonna change. So far, that's all. G times A is going to be, let's go back up here, G times H. H would be some rate, right? So what would the H would be? This one out, we do it. When you make that times this, will give us 1 over. Over. So we usually write it, yeah, but here's what that means. If I take the derivative of this, I get to the energy. I take energy, taking it back. Okay?
Okay.
Let's hold off with this part for right now. So what we're gonna have to deal with, and we read this a lot, is you've got this weird connection between intervals and derivatives, but also you've got the fact that my gravity is changing. So my potential energy is going to be a lot more calculator heavy. than it was previously. Now, the weird question on these is what happens if your R is actually still inside the Earth? But it works. Because you're considering zero to be the center of the Earth, so there's not gonna be any weirdnesses like I can't get a negative distance. You won't have a negative distance because it will be negative center of the Earth. Conversely, what this also means is when you launch something into space, it may be going 28,000 miles an hour, and kinetic energy is 1/2 mv squared. It's great and all, but in space, this R is so big that every object in space has a negative potential energy because it has way more stored energy in the gravitational field than it does in the kinetic energy going out. Does that make sense? Okay. Well, remember that
I was
because of
with you,
yeah.
and then I wasn't.
Well, what we've got is
That happens a lot.
if here's your satellite, right?
Yes.
If we have a satellite there, your MGH here, H is going to be tremendously large.
I agree.
So when you do your total energy, that would be U plus K. U will be a much, much larger value than, and since in terms of energy, this is stored, this would be a negative number of some sort, or a positive number of some sort, and that would be a win. So your energy of your satellite will be a net stored energy.
Why is it negative?
Because the way we define potential energy, right? And because what happens is your chemical
Negative.
So in essence, what have we done? By launching something into space, we've given it this much potential energy. But potential energy in terms of energy is a negative value because it's stored. So when we take potential, negative number, plus kinetic, always a positive number, you end up with a net negative.
Okay.
And part of that is due to the fact that when you integrate this, it's a negative power. So you get a negative sign due to the negative power.
Whenever we just did the energy, like before we erased it.
It was positive if I, depending on how I put my zero.
Okay.
If you put your zero at the center of the Earth, then this will be negative. Because you have taken energy out. See, this, in physics 1, I didn't have to do that. I didn't have to talk about the fact that potential energy is negative. But like right now, this marker has a negative potential energy because gravity is pulling down, but the object got moved up. So the work done by gravity is a negative amount of work. The work done by me is a positive amount of work.
Yeah.
You see where that's going?
Yeah.
So it's who's doing the work. Gravity's applying a force on it, but the object moves in the opposite direction of gravitational force. Since work is a dot product, force times distance, you get a negative sign for this. Okay?
Okay.
So there. And then you have to be careful because DG is not gold cheap. I don't think that's gonna be a problem for you. Like that, I don't worry about that problem. I worry more about this problem.
Yeah.
Is that we can't just say like, oh, this has 10 joules of potential energy and it's moving with 40 joules of kinetic energy, so it's got 50 joules total. It does not. It has negative 10 plus 50, right? Negative 10 plus whatever I said. And so you got to keep the sign, you have to deal with the signs now that you're in physics. You didn't have to before. But if you'll recall, every time I did these problems, it was always changing you the extra value and changing it.
Yeah.
Because we ignored the sign. But here, it's actually, if you change potential, going from here to here, this would be U final minus U initial, right? That's how you normally get changed.
Yeah.
But in the integral, to fix this to be the center because of the way the work is done, it's a negative word, which flips the sign.
Yeah. Yeah.
And so then that becomes when I have NG file. And NG original,
Yeah.
yeah. And so because you retracted here, you never saw that. Okay. That's fine. I'll let you soak on that a little bit, let's get that erased real quick. Okay?
Okay.
All right, I'm gonna go check on these folks.
Also, Owen and I.
Okay, all these folks are gone, so it's all good.
Owen and I need cross products explained.
Okay.
But luckily, I get to be here for a week.